So this is probably maybe if I do it really easy, that's fine, that's good. All right, so, oops. All right, so we did number one. Where is F continuous? Am I on the right page here? Yeah. Where is F continuous? Everywhere but -3, -1, 1, 2, 4, right? You just list I mean, you could list everywhere but those, or you could just list from -4 to -3, from -3 to -1, that kind of thing, right? And then G continuous, same thing, okay? So the idea is understanding what is continuous. Okay, starting with number 7. Does the conclusion of the intermediate value theorem hold from -4 to 4? Now, Emily and I were discussing that a little bit yesterday, and let me pull back up this notes from yesterday. Okay, so does the conclusion hold is saying, does this part hold? In other words, does it hit all the y values? Between what? Does it hit all the y values between the endpoints? That's really key. So on number 7, the endpoints are, yes, do I have, I should have, I'm not very prepared this morning. I've been here for an hour and a half. Why do I not? I wonder if I have the picture. Probably don't. I'm afraid. There it is. Perfect. That's what I wanted. Okay. So does it hit? So the key is between here and here. That is what most people don't understand about this one. Okay. On number 7. A lot of people look at this. Does the intermediate value theorem conclusion hold? The conclusion of the intermediate value theorem is the last part, the part that says it hits all the y values, right? A lot of people think it's got to hit them all the way up to the max, right? It's not. No, it's between the endpoints. It's between f of -4 and f of 4. Here's f of 4 and here's f of -4. So does it hit all the y values between here and here? And it does, right? Is it guaranteed to? It's not guaranteed to, right? Because this is not a continuous function. If it's a continuous function, it's guaranteed to. But this one's not. But it does hit them all. Like right here, there's a hole, but there's that point right there. Okay, you go on up here, it hits all the rest of them all the way up to here, which has got that point, that point. Okay, so you got to understand, the intermediate value theorem says if you start here and you end here, it's got to hit all the points in between those. Very subtle difference, but people sometimes miss it. Does it hold on G? So here's our starting point, here's our ending point. So does it hit all the y values between here and here? I think it does, right? Just this piece alone goes all the way up to there. Okay? So it does, even though it's not guaranteed to. So that's like your parents bought you the car even though you didn't get it in. Right? So we did hit all the y values, but we wouldn't have had to because the theorem doesn't promise. How about the extreme value theorem? What's the conclusion of the extreme value theorem? That there's a max and a min. So on f, from -4 to 4, is there a max? 2. Is there a min? -2. So yeah, there's both a max and a min, even though there's no promise that there would be. What about G? Is there a max? Yeah, 2. Is there a min? No, there's not a min here because it could be -1.9. Oh wait, -1.99. Oh wait, -1.999. Oh wait, -1.9999. No matter what, I can always go a little lower, a little lower, a little lower. There's no min value. Okay, so that's what you would have to explain that and so forth. Okay, 11, 1 over x. So the graph of 1 over x. So here's 1 over x, like that. Okay, that's one branch of it anyway. The other branch is over here. Okay. What does the extreme value theorem say on the interval 0.1 to 1? Is that continuous? Is that a closed interval? So therefore, the extreme value theorem's got to say there's got to be both a max and a min. There's got to be both a max and a min. That's what the extreme value theorem says. Because it's continuous on a closed interval, you'd have to say all that, right? Although f is continuous from 1 to infinity, so if I look at it from here on out, it's continuous, no breaks, no holes, nothing like that. There is no minimum. It just keeps going down, 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 closer, closer to 0. Why does this not contradict the extreme value? It's not a closed interval. Easy, easy. Although f is continuous from 0 to 1, this part here, there's no maximum. Same thing, not a closed interval. Not a closed interval. 14. What does the extreme value theorem say about f on the interval 0 to 1? So what if you do close the interval? What if you do look from 0 to 1? What does the extreme value theorem say? Because there's not a max. But that's not a number. So you can't have infinity. So you haven't answered the question. What does the extreme value theorem say about f on the interval 0 to 1? No. No. Well, you're getting to the justification. What does the extreme value theorem say about this function on the closed interval 0 to 1? Nothing. It doesn't say anything about it. Because it's not continuous. Right? It doesn't say anything. The extreme value theorem only says you will have a max and a min if the function's continuous on a closed interval. This is not continuous because there's no value at 0. Right? There's no value at 0. So it's not continuous on the closed interval 0 to 1. Because it's undefined at 0. So if the hypothesis is not met, the conclusion doesn't say anything. The theorem doesn't say anything. That's your answer, right? So you're right when you said there's both a max and min. Right, the extreme value theorem is going to do one of two things. It's going to either say there's a max or a min, if the function's continuous on a closed interval, or it's going to say nothing. It's one of those two choices. Right? It's either going to say, so when they say, what does the extreme value theorem say about this function on this interval? It's either going to say there's both a max and min, or it's going to say nothing. And in this case, it says nothing. Okay? 15. Although f of -1 is -1, right here, and f of 1 is 1, there is no value where f of c equals 0. In other words, there's no roots. Remember we said that the other day? Remember we did Newton's method? We said, let's plug in a -1. Oh, we get -1. Let's plug in a 1. Oh, we get 1. Hey, this thing went from here to here. Didn't it have to cross through 0? Well, does this graph ever cross through 0? No. Why doesn't this contradict the intermediate value? It's not continuous. You see the theme here? The same answers are happening over and over again, right? Okay, but this is just an example of what we were talking about. So we were talking about Newton's method. We said, hey, we got a negative here, then we got a positive here. It must have went through 0. This one didn't. This one never went through 0, right? On its way from here to here. Well, it's just not continuous. It had a jump. It had a gap, right? It went here, and then boom, it jumped up to here, right? Not continuous. So it's not continuous. We don't have that promise. Okay, show that the intermediate value theorem holds. Okay, here's where you might, on our quiz, might do a little bit of calculating. So 0.1, so this is 0.110, I guess, and then this would be the 0.11, and y equals 5. So y equals 5 would be right in here, right? So it says show that the intermediate value theorem holds for f. In other words, show that there's some point where you get a y of 5. Show that it goes through 5. What would you do? 1 over x equals 5. You just solve it. 1 over x equals 5. So 1 equals 5x. X equals 1/5, which is 0.2. And sure enough, that's in between 0.1 and 1. So we just found an x value between 0.1 and 1. And that works, showed it. That works, showed it. Okay. So we picked, remember, what does it say? It says let K be any value between f of A and f of B. So 10 and 1. So let K be any value between there. We should be able to find an X that makes it work. So pick any value between 1 and 10. We should be able to set it equal to 1 over X. And we should be able to find a value that's in between 0.1 and 1. There you go. Okay, so there you might have a little bit of calculator to do solving on this quiz on Friday. This no calculator kind of quiz. But it, might have a little solving. 17, show that the IVT, or no, did we do 17? We didn't do 17. 18. Okay, the temperature is 13 degrees, and then at midnight, and then it went up to 15 degrees at 6 a.m. What does the intermediate value theorem say about the temperature during this time? Had to hit all those temperatures between 13 and 15. It had to be 13.1 at some point, 14.7, right? Had to hit all those because it's continuous. It says explain why those are fulfilled. So it's always important whenever you do these theorems that you talk about why it's continuous, why it's a closed interval, whatever. Midnight to 6 a.m. is a closed interval, and temperature is a continuous, right? Is a continuous thing, right? It's going to go. It's not going to instantly jump, right, and skip over. It may rapidly change, but it's not going to do all. Must there be a time between midnight and 6 when the temperature was 10? Could there have been a time? It's kind of like the Elm Creek. I go from Kearney to Grand Island. Could I have been in Elm Creek? Could have. But we know I went from Kearney to Grand Island. We got to hit all those temperatures, but we don't know. Maybe it went down to 10 and then went back up to 15. Could have, but we don't know. Must there be a time between midnight and 6 when the temp was an integer multiple of pi? Kind of a weird one, but I don't think so. 3 pi is going to be like 9 something. 4 pi is going to be 12 something, right? And then 5 pi is going to be over 15, right? So there's 12 to 15. We know it's 13 to 15, and so you would say no. What does the extreme value theorem say about the temperature? It's the only thing the extreme value theorem can say, right? There's got to be a max and a min, because this is continuous on a closed interval. There had to have been a highest temp, there had to be a lowest temp during that time, which makes sense. Could the temperature have been 25 degrees? Sure. All right. So just all variety of different questions. Okay, 22. There were 37 people in the class 7 days ago, now there are 12. That's kind of like calculus. 37 people in the class 7 days ago, now there are 12. Does that say anything? Does the intermediate value theorem say anything about that? Why not? Not continuous, right? Number of people, that's a discrete, right? You have 2 people, 3 people, 4 people, you don't have 3.5, 3.1, right? It's not continuous. 37 miles from home, now I'm 12 miles from home. You had to hit all those different distances between 37 and 12, right? That's what the intermediate value theorem would say. At some point in time, you were all those different distances away from home, because it is continuous. I was driving 37 miles per hour, now I'm 12 miles per hour. Again, you had to hit all those speeds in between. It is a continuous situation. I had $37 in my pocket, now I have 12. Doesn't say anything, right? Doesn't say anything, it's not continuous, okay? So just, a lot of different ways, but just, so be sure you can state those theorems and then answer these questions about those different conclusions and so forth. Okay, so let's get your packets out and let's talk about a few of those things, see if there's any of those. We can go back to sample 1 if there's anything you want to revisit there. Anything sample 1 or sample 2? Sample 1. population grows according to this function, this equation for t is positive. Population will approach a limiting value as time goes on. During which year will the population reach half the limiting value? So it's just, we just want to know when this population will equal half the limiting value. So, and this is a calculator problem, right? So equals what? So we got to know what the limiting value is, right? So what is it? Anybody know? Jesse, what'd you say? The limiting value is 3,000? How would we get it? How would we get the limiting value as time goes on? Did a graph. Okay, it's a calculator problem. Why not? Sure. What else? I would say it wouldn't need to take that much time, to graph it, quite honestly. How else could you figure out the limiting value? Come on, think of the word. Limiting value. Huh? What limit? As time goes on. As t approaches infinity. As time goes on, right? As t gets bigger and bigger and bigger and bigger. As t gets bigger and bigger and bigger, what's going to happen? Isn't this going to zero? This part right here? As t gets bigger and bigger and bigger, what do you got? E to the negative, right? Which is 1 over e to the something positive, right? Which is 0, right? 1 over something really big is going to get really small. This whole piece right here is just going to go to nothing. Yeah. So it's 6,000. Now, you do have the calculator, but trust me, this could be on a no calculator part real easy, right? This idea could be on a no calculator part real easy. You got to be able to look at e to a negative and know that that goes down, 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 goes to 0, right? So as time goes on, the population is going to get closer and closer to 6,000. So, half the limiting value is 3,000. Now, since it is a calculator one, you just go to your calculator and solve it. Just do a solve on your calculator. And I think it comes out 3.8 or something like that. So what year is that? That'd be the 4th year. That'd be the 4th. Right? But then you just do a solve. But yeah, that's the kind of stuff, problems like that are exactly why we do these packets and why we, prepare for this AP test, because that's the kind of questions they ask. So it's we didn't have a question like that on our quiz when we did limits, but you got to understand that is what's happening there, right? But now as far as a test taking strategy though, if this is the calculator section, you're allowed to use it. Graph that thing to see. I have no problem with that. That's good. Okay. Now, did you just trace and kind of find where 3,000 was then when you did that, or did you actually set this up and do a solve then?
I just trace.
Put a pig in to get the 6,000. But then, once you knew that was 6,000, then what'd you do? Did you just trace back to about 3,000 and kind of see what year it was, or did you do a solve? Okay. Again, help yourself out with the answer books, but like we're going to have a bunch of work time today. Really spend as much time as you possibly can trying to figure these out. If you get stuck in one, skip it, go on. Don't run right to the answer book right away and write stuff down. Skip it, think about it, come back, try things, and then check, and see what happens. Okay, what else? Anything else in sample 1? Yeah, in the free response. Okay, tell me what you've done, because I kind of gave you a hint, didn't I? Kind of helped you start it.
Yeah, I don't, what did you say that to do?
Okay. Well, all right, we have this hill. Here's this parabola right here. Right? And this is a no calculus, right? No calculus. All right. So we've got this tower on top of the hill, and this is the line of sight down to this point here. Here's the base of the hill. Now, I'm skipping to part B. Part B, they want to know this distance right here, right? So we're going to need to find these different points, right? But I say we know some of these points. I think we can already write some of these points. I mean, we know this point is something 0, right? What do we know about, right? This part, we should be able to do for sure, right? What's this point? How would we find that point? When x is 0, right? Okay. What about this point right here? That's when x is 0. What's that? Okay, what about this point? This point's also 0 something. Okay. What about this point right here? Okay. The Shanghai problem is 2 different ways of doing slope, right? One is a derivative, so you got this parabola, so the derivative of that would be the slope. And another would be the slope between 2 points, right? Now this point we don't know, but I would say we do know this point. I think we do know this point. I think we do know this point. But I'm not going to do it for you. It's really easy. This is on the parabola. There's the parabola equation, so you can find that point. This point's on the parabola, so you can find that point. You know the tower is 16 foot tall, so this little distance here is 16 feet, okay? So you can find all that, okay? And then you got enough points, you can do slope between 2 points. You can do the derivative. You can set those equal, okay? It's all okay with that much right there. So what they wanted in part A, they first want the equation of this line. So once you do your derivative, you get once you find your slope, you can do that. Then you've got points, you got plenty of points there, you can find the point. So once you have the equation of that line, then you can find this point down here. And then you got what you want. If you got this point, you got this point. Once you find the equation line, you got those 2 points, you know what that distance. Okay? All right. We've done enough Shanghai problems, you guys can set that up from there, and you can find those points. Okay. And then once you have some work down and you've tried some things, then and you still don't get it, then ask me again. Have you set up anything on that yet, Emily?
But I know I can just put 0 and full line and those points.
Right, exactly. So you go through that, you get that far, then see what you need. Yeah. Is that mine? Where'd that come from?
So that's
I didn't miss it. And I love it.
Don't mention me.
Okay, I love it. Thank you. Okay, another one. Sample 2. Oh, look at that. That was right on. Weird. Okay, tell me what you've done so far. Okay, so we want the normal line, and it tells us right here the normal line is perpendicular to the tangent line, so that's just opposite reciprocal slope, right? So you did the derivative to get your slope. I like that. Now this would be x squared minus 1 to the 1/3 power. So you did your derivative. Tell me what that was. What about to the negative 2/3? Okay, did subtract the power. So bring down the 1/3, x squared minus 1 to the negative 2/3, and then times 2x. Now that would simplify to the 2x would be on top, and then the bottom would have a 3, and then would have x squared minus 1 to the 2/3. That would be your derivative right there. Okay. So that would be an arrangement. It's kind of funny. I'm just my algebra 1B class. We're just going to start talking about negative exponents, flipping things around and stuff. Reminds me how important that is, like even in a problem like this. But then they say where x is 3, right? So we're going to put a 3 in there. So we're going to get 6 on top. We put a 3 here. 9 minus 1 is 8. Here you do the cube root of 8 is 2. 2 squared is 4. And then 4 times 3 is 12. So 6 twelfths is 1/2. So there's our slope, 1/2. But that's for the tangent line. So what's the slope of the normal line? -2, right? Absolute reciprocal. So the line we're looking for has a slope -2, and then x minus 3, and then plus. Now I need my y point. How do I get my y point? Put 3 back into the original. So 9 minus 1 is 8. Cube root of 8 is 2. So I get that. So I get y equals -2x plus 8. Doesn't look like any of those. I'll add the 2x over there. Y plus 2x equals 8. So normal line, I mean, should know a normal line is perpendicular to a tangent line. If you didn't, now you know. Usually when I've seen that problem, we tell you. Maybe not. Okay, what else? Okay. 27, this one right here. Which graph best represents the position if the particle's velocity and acceleration are both positive? What is it? The velocity is positive. There's several ways to think about it. Velocity is the slope. So if you're going position, velocity, acceleration. This is positive and this is positive. What does velocity positive tell you about position? This is F, this is the chart. So if this, no. If velocity is positive, what's this? No. Increasing, there you go. This one's positive, this is increasing. If this one's positive, concave up. So it's got to be positive and concave up. So the only one of those that's positive, or excuse me, increasing and concave up. So the only one that's increasing concave up. Or you can just think it through and say, okay, if velocity is positive, it's going in the positive direction, and if the acceleration is positive, it's increasing its velocity. And so it's going faster and faster and faster. You just think your way through it there. But you could also do it with the calculator. Okay? All right, well, here's what we're going to do. If you got some questions you can ask, I'm going to give you the rest of the time to work. We should be finishing sample 2. I mean, yesterday I gave you the 4.8, but I said you should be working in sample 2. So I would say we should finish sample 2 for sure. I've got the 3rd packet sitting right here. And now you'll notice this one at the top says, just doesn't say sample like yours on the front page says sample exam, great big. Sample exam 1, sample exam 2. This just says exam 2. So that's what I'll call this. So that's sample 1 and sample 2. This is exam 2. Okay, so that's the next one. You can take one, not take one yet, I don't care.